So today I want to look at limit properties and do more evaluating of limits. Okay, but first, some bell work. Here's a graph. Am I going to give you a graph? Oh, I see. Okay, the bell work is to graph this. Graph f of x. And here's what we know about f of x. F of x equals 1 minus x for x's between 1 and 0. And then the constant 1 for x values from 1 to 2. And 2 for x equal to 2. And x minus 1, or is that negative x minus 1? Nope, it's just x minus 1 for x values between 2 and 3. And finally, let's have one more piece. 5 minus x for x values from 3 to 4. Hot dog! So, our piecewise function comes in 5 pieces. Please graph this function. Pause the video, give it a try. I can't wait to see what you come up with, and that's a 0. Welcome back. So here's 0, here's 1, here's 2, here's 3, here's 4. So we're going from 0 to 4. So from 0 to 1, it looks like this line with a slope of -1 and a y value of 1. So I believe that's it. If I plug in a 1, I get 0. If I plug in a 0, I get 1. That's closed circle there and open circle there. Now, for 1 to 2, I'm just going to have this to here. From at x equals 2, I have a y value of 2. 1, 2. And then from 2 to 3, x minus 1. Okay, so x minus 1. If I plug in a 2, I get 1. If I plug in a 3, I get 2. And an open circle on the left, but closed circle on the right. And finally, 5 minus x for the x values between 3 and 4. If I plug a 3 in there, 5 minus 3 is 2. Good, that's that point. If I plug a 4 in there, 5 minus 4 is 1. So I'll go back down to here. So there's my graph of f of x. Good? Okay, so now that we have this graph, what's the limit as x approaches 1 from the positive side of f of x? What y value are we approaching on f of x as the x values get closer to 1 from the positive side? That's me coming in this way. Don't look over here. Look over here. I want to approach 1. I don't want to go take an excursion. Approach 1. I have a value of 1. And what about the limit as x approaches 1 from the negative side of f of x? What happens if I come in from this direction? Well, the y values are heading down to 1. I'm sorry, heading down to 0. So, does the limit as x approaches 1 exist? And you say, no. Why not? Because the limit as x approaches 1 from the positive does not equal the limit as x approaches 1 from the negative side of that function. Okay? Write that sentence. Justify your statement. So we've got this limit, we've got this limit, we know this limit doesn't exist. We do know that f of 1 equals 1 from that point there. All right, well, let's take a look at some other limits here in this picture. And now that we have the graph, we don't need the f of x. Okay, so how about this limit? The limit as x approaches 2 of f of x. And let's do from the positive. And the limit as x approaches 2 from the negative. And what about the limit as x approaches 2? And for good measure, what about f of 2? Because I plug in that x and I get out a y value. So what do you get for the value of the limit as x approaches 2 from the positive? As we come in from this direction, what y value are we approaching? Well, we seem to be coming down towards y equals 1. And if the limit of f of x as x approaches 2 from the negative side, as we come in from this direction, what y value are we approaching? Well, we're on the same y value for that whole time, and that's a y value of 1. So what about the limit as x approaches 2 of f of x? Well, that's 1, because these are both 1 and they're equal to each other. Finally, f of 2 is not 1. F of 2 is 2. The value of the point at 2 is 2. Okay? How about we do one more? Maybe 2. The limit as x heads to 3 from the positive side. The limit as x approaches 3 from the negative side. What do you get? And does the limit as x approaches 3 exist? Why or why not? Okay, well, let's see what we can say. The limit as x approaches 3 from the positive side. So as I come in from this direction, what y value am I approaching? A y value of 2. The limit of f of x as x heads to 3 from the negative side. As we come in from this side, what y value are we approaching? 2. Does the limit as x approaches 3 of f of x exist? Yes. The limit as x approaches 3 of f exists because the limit as x approaches 3 from the negative side equals the limit as x approaches 3 from the positive side. Don't forget to put the function there. If you do this, I say I don't know what you're talking about. The limit of what? Well, it's the limit of f. So put f. Don't skip that. Okay? Excellent. So let's move on to limit properties. And just like learning properties in middle school where they said a plus b equals b plus a, and you said, duh, why would I need the commutative property of addition? And then it turns out you're looking at something like the square root of 3 minus x, saying, how am I supposed to graph that? When Kukla says, hey, why don't you do negative x plus 3? Using the commutative property of addition, I know to subtract 3's and then divide the x's by 1. Whereas I might not see that here, and it's the commutative property of addition that allows me to flip those two. So, even though some of these properties may seem really obvious, great, let it be that way that you can use them. All right, so these properties always work. Always, if precondition both the limit as x approaches c of f of x equals L and the limit as x approaches c of g of x equals m. Okay? So these limits exist. I'm giving them to you. And then I know that whenever I see these limits, I know that the property, the limit property that I'm using them in, that is guaranteed to work because these limits exist. I don't know what they are, but I don't really care because I'm talking about a general case. So our first obvious limit property is the limit as x approaches c of f of x plus g of x is simply L plus M. Huh? How'd you do that? Well, the limit as x approaches c of f of x, we said, was L. And the limit as x approaches c of g of x, we said was m. So really what we're thinking about doing here is saying the limit as x approaches c of f plus the limit as x approaches c of g. So I can split this up into these two limits and then add those limits together. Now, not only does this work here with addition, but we've also got the limit as x approaches c of f over g. And that's going to be, oops, sorry, we just did addition, I need subtraction, f minus g. Well, we know the limit as x approaches c of f is L, and we know the limit as x approaches c of g is m, and so I can understand this limit of this difference as the difference in the limits. I could take the time if I wanted to, and I almost never want to take this intermediate step. Because I know from definition up here, this is L, I know from the definition up here, this is M, and I see the minus in between them, okay? And again, it's just a basic property. I'm not going to worry about it's not harder than you think it is. That's what I want to say. So, third property, the limit as x approaches c of f times g. Do you have a thought of what this is going to be? Why, that's right, L times m. Because I can understand this as the limit as x approaches c of f times the limit as x approaches c of g. This is L, this is m, and so I get L times m. Fabulous. And what's next? Well, instead of multiplying two functions, what if we have limit as x approaches c of k, some constant, times f of x? Well, that's going to be easy, because that's just going to be the same as k times the limit as x approaches c of f of x. In fact, you could even write this as the limit as x approaches c of k times that limit. Now, what did we say the limit of a constant was? We said it was the constant times the limit as x approaches c of f of x. And we know that this is equal to L. So I've got k times L. This is equal to k times L. Okay, so that's a constant multiple. Now, we've got two more. The limit as, I guess this is 5. 1, 2, 3, 4, 5. The limit as x approaches c of f of x over g of x. So this is going to work out to be L over m, but m can't be equal to 0. Okay, if m is equal to 0, our limit is undefined. So I don't think you have to worry about that so much. Like you don't have to write this down. You just have to recognize, oh my goodness, I can't have a 0 in the denominator. Okay, the last property, 6, the limit as x approaches c of f of x raised to the r over s power. Well, this is going to be L raised to the r over s power. That's all. Okay, these limit properties really are kind of obvious. But let's do some stuff with them now. All right? All right, so how about the limit as x approaches 0 of x over sine x? Okay? And I'd like to know what this limit is equal to. Well, I'm actually going to use this limit property. The limit as x approaches c of f over g equals L over m. Okay. Now, how am I going to use that? Well, here's what I want to think about. Let's evaluate this limit. The limit as x heads to 0 of 1 over sine x over x. Okay. So this is the limit of a constant on top, and on the bottom we have the limit of this function. All right. Now, where am I going with that? Well, I know that I'm going to do the flip and multiply and get to this, but I should be able to evaluate this. Well, let's see. Yeah, no. I'm not sure how to do this. Huh. By using this limit. Well, I know that's supposed to be 1, but I'm supposed to be using this to show me that. So how do I do that? Using these properties. Well, I know the top is 1, and I don't know what that is. But due to direct substitution, I get 0 over 0. And so I'm that face. Huh. Well, I think I'm going to have to do a little more research and find out what I was talking about then. Oh, look. Here's my note to do this. And then there's the little note saying, huh? So clearly, I've been stuck on this desert island a couple of times. I'll get back to you on using that limit property. All right, how about this one? The limit as x approaches 2 of x squared over 2x. Well, so I can split this up into the limit as x approaches 2 of x squared divided by the limit as x approaches 2 of 2x. Okay, so this is going to be 2 squared, or 4. This is going to be 2 times 2, or 4. I get 4 over 4, which equals 1. See, I used that division limit property. Now, what would have happened? Oh, I could do direct substitution and not need that limit property, right? And so why would I ever use that limit property? Trust me, it's going to come up. You're going to use it. So what are my methods of evaluating limits? Well, favorite is direct substitution. Hey, actually, why don't you fill out the rest of this list? Aside from direct substitution, what other methods do we have to evaluate a limit? Two, good. We want to, when direct substitution doesn't work, we want to rewrite using algebra skills. 3, I'm thinking about using a table. 4, I'm thinking about using a graph. What else do we have? What else do we have besides direct substitution? Rewriting with our algebra, using a table, using a graph. Well, use the limit properties. So all of these are going to be tools that I can use to evaluate limits. All right, so let's see if we can see something. All right, the limit as x approaches 0 of cosine x. What's that limit going to be equal to? Remember, we want to know what the y value is on cosine as x approaches 0. Cosine of 0 is 1. Direct substitution worked there, no problem. How about the limit as x approaches 0 of sine x? Again, direct substitution, no problem. But when I come to something like the limit as x approaches 0 of sine x over x, when I do direct substitution, I have the sine of 0 over 0. Well, that's an indeterminate form. Okay, so do we have some algebra to make this work? There is some algebra. I could use a Taylor series here, but you're not going to learn about Taylor series until you take Calc 2. So I'm not going to worry about that right now. What I am going to say is I don't have an algebraic way to rewrite this to get some value for this limit. I'll tell you that that limit is equal to 1, but I can't know that seemingly with just my algebra skills. So what if I use a table? So I go over to my function and I type in sine x divided by x, and then I go to my table and I want to type in values that are approaching 0. So how about negative 1, negative 0.1, negative 0.01, negative 0.001. Am I approaching a y value? Negative 0.00001. And if I arrow onto those, I see that I'm not yet at 1, but I'm definitely approaching 1. So, oh, and that was only from the negative side. What about from the positive side? 1, 0.1, 0.01, 0.001, 0.00001. What value am I approaching? Well, these y values are approaching 1. So I can know by looking at a table that this limit is equal to 1. I could also come over here to my graph, and if I do zoom standard, as x approaches 0, what's the value? We'll see as x approaches 0, I seem to be a value of 1. But let's just confirm that by going and changing our window 1 to 2 graph. Yeah, so that's 2, that's 1, that's 0, and the limit is 1. Now, here's an interesting thing. At 0, I plug in a 0 there, I have a 0 in the denominator. Where's the, what, is that, shouldn't that be a vertical asymptote? Is there a hole? What's happening here? So let's take out the axes for a second. I'm going to go up to Format and turn the axes off, and then graph. Oh, look. There's a hole. There's a hole at x equals 3. But we know that the point doesn't exist in order to have the limit exist. This limit, the limit of sine x over x as x approaches 0, I'm approaching a y value of 1 from both sides. So I can use a table or graph to evaluate this limit. But now I'm going to say we know this limit. Okay, this limit is 1. This is a known limit. And by the way, this will come up a bunch. So now that we have that limit, what can we say about this limit? The limit as x approaches 0 of x over sine x. What's that limit going to be equal to? Well, if I do direct substitution again I get 0 over 0. But what if I think about this as the limit as x approaches 0? Oh, so this is the one I'm trying to figure out. And I'm saying, hey, that'll be the same as the limit as x approaches 0 of 1 over sine x over x, right? I know this one, so I want to use it. But I have to turn this into something that uses that. So I'm using that property, that f over g property, to evaluate this limit. Now that's going to be the limit as x approaches 0 of 1 divided by the limit as x approaches 0 of sine x over x. What's the limit of a constant? The limit of the constant is 1. What's the limit as x approaches 0 of sine x over x? Oh, we know that. That's 1. And so we get 1 here. Okay? So I can use my properties to evaluate. Next, how about the limit as x approaches 0 of sine 3x over 3x? Again, when I do direct substitution, I get 0 over 0. So is this going to be 1? Is this going to be 3? Is it going to be 1/3? I don't know. Well, here's what I know. Let's make a equal to 3x. Now let's rewrite this limit with a's instead of x's. Okay, so the limit as a over 3 heads to 0, because we're not using x. We have to solve this equation for x, of sine a over a. Well, so the limit as we approach 0 of this, well, what was this? That was 1. Remember, we had that definition on the last board. So, yeah, I'm good to know that that's 1 there. However, if I have the limit as x approaches 0 of sine 3x over not 3x, but x, now I have a problem, because I can't make that substitution in both of these places to turn it into sine a over a. So what do I need? Well, I need this and this to be the same. I need this and this to be the same. So what I'm going to do is, because I'm an American, I'm just going to multiply that damn thing by 3. But we know that we need to never just multiply the bottom by 3, or else the top will start complaining. 3 over 3 is a form of 1. I'm multiplying this fraction by 1. That's not a big deal. But if I just multiply the denominator by 3, that's a big deal. So what can we say here? Well, now I can split this up into 2 limits. I can say that this is the limit as x approaches 0 of 3 times the limit as x approaches 0 of sine 3x over 3x. We know this limit is equal to 1, and we know that the limit of a constant is the constant. So this limit is 3. Oh, no, not that limit. This limit is 3. The limit as x approaches 0 of sine 3x over 3 is 3. Okay. So, you ready for one unit? How about I do one more? The limit as x approaches 0 of sine 5x over sine 3x. Okay? So, if I do direct substitution, I get 0 over 0, and I'm set. So instead, I think about, well, I know that the limit as x approaches 0 of sine x over x, in fact, u equals the limit as u approaches 0 of u over sine u. But both of these cases we showed on the last board were equal to 1. Okay? And in order to do this, I need this and this to be the same. This and this have to be the same. Well, I don't have that. So I'm going to think about breaking this thing up into sine of 5x times 1 over sine of 3x. In fact, I'm even going to use this limit property. X approaches 0 of 1 over sine 3x. Now, in order to use these properties, these things that I know, the bottom needs to have a 5x. However, I can't just randomly multiply denominators by 5x. So simultaneously, I'm going to multiply the top by 5x. And over here, I really need a 3x on top. I need these to be the same. But I can't just randomly multiply numerators by 3x unless I also multiply denominators by 3x. So what do we have here? Well, I'm going to write it this way. The limit as x approaches 0 of 5x times the limit as x approaches 0 of sine 5x over 5x times the limit as x approaches 0 of 3x over sine 3x times the limit as x approaches 0 of 1 over 3x. Good. Nice. Now what about this? What's this limit equal to? Well, remember, when these are the same and I'm approaching 0, that's 1. What about this limit? Well, we remember that as u approaches 0 and these are the same, that's 1. So these are both 1. And these, I don't want to put 0 in because I'm going to have 0 on top, 0 on the bottom. I'm going to be sad face again. But what I can do is bring these together and write 5x over 3x. So putting these together in this limit, this one was 1 and this one was 1. Now here, I can cancel. And what's the limit of a constant 5/3 as x approaches 0? Well, that's 5/3 times 1 times 1 is 5/3. So I know that this limit is 5/3. Fabulous. Wow, I really had to use my properties there to break things up, to evaluate. So how about you do this one? The limit as x heads to 0 of sine x minus 2x over x. Okay, so try this one out, pause the video, give it a try, come back if you have questions, or when you're done. So did you try, welcome back by the way, did you try plugging in the 0 and getting that 0 over 0 indeterminate form thing? Yeah, me too. So instead, what I'm going to do is I'm going to use my algebra skills to rewrite this, to split this fraction up into two pieces. Like that. Now we know this limit from using the table in our graph is 1. And here, I can cancel those out. So now I have the limit as x approaches 0 of 2. This is the limit of a constant. What's the limit of the constant? The constant. So this is 1 minus 2, or negative 1. This is negative 1. Make sense? All right, how about this one? The limit as x approaches 0 of 3x plus sine 2x over x. Will you please evaluate that one? Welcome back. So did you split this up into the limit as x approaches 0 of 3x over x plus the limit as x approaches 0 of sine 2x over x? Because when you plugged in 0, you got 0 over 0, and knew that was an indeterminate form. Good. So what can we do here? Well, I can cancel those, and now this is just going to be the limit as x approaches 0 of 3 plus, and what can we do here? Well, I remember that these need to be the same. And if I can make these to be the same, then the limit of this as x approaches 0 is going to be 1. So how am I going to do that? Well, I'm going to multiply the bottom by 2, so they can be the same. But if you're going to multiply the bottom by 2, you also have to multiply the top by 2. So now I'm going to have the limit as x approaches 0 of 2 times the limit as x approaches 0 of sine 2x over 2x. All right, so what do we know? We know the limit of a constant is the constant. We know the limit of a constant is that constant. And over here, the limit as x approaches 0 of sine u over u is 1. So I get 3 plus 2, 4, 5. This limit is 5. Okay? What about this one? The limit as x approaches 0 of sine squared 3x over 3x. All right, why don't you give this one a try? Come back when you're done or if you're stuck. All right, so did you say, hey, these are the same, this limit is equal to 1? Yeah, that's kind of problematic because of the squared. So let's take a look and see what we could do with that squared. I mean, it's already 0 over 0, so I know I got to do something to it. So let's say that sine squared is sine 3x times sine 3x over 3x. Well, then I can write this as the limit as x approaches 0, sine 3x over 3x times the limit as x approaches 0 of sine 3x. Right? I'm splitting up that squaring into sine 3x is being multiplied. And then I'm going to split this into two limits, one here and one here, and evaluate each of these separately. Now, what did we say the limit as x approaches 0 of sine u over u was? 1. And what about over here? Can I do direct substitution? 3 times 0 is 0. The sine of 0 is 0. Yes. And so I get 0. This limit is 0. All right? So we can evaluate limits. We talked about 4 methods, 5 methods for evaluating limits. We said we can evaluate limits in lots of different ways. 1, direct substitution. 2, rewrite algebraically. 3, use a table. 4, use the graph. 5 are limit properties. Can help. And that seems like a lot of things that we could use to evaluate a limit. However, there's more. So one is to use a power series. We won't be doing this in our class. This is a Calc 2 topic, but since we're talking about evaluating limits, I'm going to show you how to use a power series to do that. You don't have to worry about taking notes on this power series, but I can show you that. And 7, use the sandwich theorem. And I'll show you that too. And here's the thing. 2 years ago, AP put a sandwich theorem problem on the free response, even though sandwich theorem wasn't in their curriculum explicitly. So we will touch on the sandwich theorem later in the year with a much easier example than the one I'm going to show you, which may well blow your mind. Okay, so let's look at power series. Remember how when we had the limit as x approaches 0 of sine x over x, and we didn't know what that was because direct substitution didn't work and I didn't have an algebraic rewrite for it, but we were able to see by looking at the graph and by using the table that this limit was equal to 1. Well, I'd like to prove that another way. And to do that, I want to use a power series substitution. This is kind of freaky and amazing. Sine x can be approximated by x minus x to the third over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial on negative pi to pi. Well, that's great because I want something smack dab in the middle of that interval. No, really, how did we figure this out? I gotta look and see. Okay, I'm gonna change my viewing window to go negative pi to pi. And let's make this pi over 2. Now, what about the y values? Well, we think that this limit is 0 at 1. So I think negative 1 to 2 should be enough for us, right? Now, over here, I'm going to graph just sine x. And in y2, I'm going to type out this power series. So x minus x to the third divided by 3. And where's 3 factorial? Parentheses 3. It's under math. And number, is it? Oh no, it's under probability. There it is. Number 4. Okay, so divide by 3 factorial plus x to the 5th divided by 5 factorial minus x to the 7th divided by 7 factorial plus x to the 9th divided by 9 factorial. Graph. There's my sine graph. Now my power function. I don't see it, but it's graphing. Do you see it here? I don't see it. What do you think that means? I think it means that one of them sits on top of the other. Let's just check that it's not like graphing somewhere outside our window by going over to the table and looking at the values. They're all the same. Sine x really is this on that interval. Freaky. All right, so I want to use this to help me evaluate that limit. And what I'm going to do is to say, okay, the limit as x approaches 0 of sine x, well, I'm not going to use sine x, I'm going to use this stuff, x minus x to the third over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial over x. Okay? So what does that get me? Well, instead of writing it this way, I'm going to write it like this. I'm going to put the x at the bottom of that fraction. Okay? So now let's simplify here. We've got the limit as x approaches 0 of 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial plus x to the 8th over 9 factorial. Yeah? And that's nifty keen because look what happens. Let's do direct substitution now. Let's plug in a 0 for all the x's. 0, 0, 0, 0. What happens to all these terms? They all go away, and I'm left with 1. This limit is equal to 1, and I can show you when I use a power series. Or I could do the same mathematical process. I'm not going to say trickery. The limit as x heads to 0 of x over sine x. I can use the same approach on this to show that that's also equal to 1. Okay, next, sandwich theorem. So the sandwich theorem is really interesting. It says, look, you've got this function, there's this value at this point, you've got this other function, and they share that value at that point, and then you've got this function. And let's say that this is x equals a. We'll say that this is f of x. We'll say that this is g of x, and that this is h of x. So I want to know the limit as x approaches a of f of x. But I don't know what it is. But I know that it's between the limit as x approaches a of h of x and squeezed on the other side by the limit as x approaches a of g of x. All right, so what I want to show is that this limit has to be between these. And now you know what I'm going to do? I'm going to say this equals that. And when I can show that these have the same limit and show that this is in between those, then I know that this must have the same limit since those are equal to each other. And not only do I have to say that, but I would also have to say, okay, so f of a, g of a, and h of a exist, and not only do they have to exist, but f of a equals g of a equals h of a. Okay? Actually, I could just probably get away with that. So the sandwich theorem is all about trying to squeeze an unknown thing in between two known things. Now in Calc 2, you're actually going to do some of these problems where you have to figure out a function for here and for here. I know, and that's the part we're definitely not going to do. We're not going anywhere near that in this class. Don't even ask me. Or watch a YouTube video if you want. But really, we won't be needing that skill in our class. We need to know this stuff. We need to know that what we're talking about is this one has to have the same y value as these other two because the limits are the same on these, and we show that this one is in between those things. Okay? So now I'm going to show you a proof of this. I'm going to show you a proof of this. Here we go. So I want to prove, well, let me just start with a picture. Let's have the unit circle. So we know that's 1, 0. We know that's 0, 1. And let's think about the line no line. No line, just this. And I'm going to have that. And I'm going to have third cone or fourth cone. Green, be my friend. And that. Okay? So what am I going to do with this? Well, I'm going to say that since this is the unit circle, this is 1, this is 1, I know that this must also be 1. All right? What else do I know? Well, I know that's a radius of the circle and that's a radius of the circle, so I know that those are the same. Good. What else? Well, let's say that this angle is x. Okay? Got a little angle there. And do you see this green triangle? So let's pull that green triangle out from there. There's x, right angle. I know this is 1. Okay? And if that angle is x, then what can I say about this? How long is this? This is the height of my triangle. Okay, so the height of my triangle is going to be, what's h? Well, I know h over 1 with respect to x would be sine x equals h, right? Because the sine of that angle is opposite over hypotenuse. Great. Now, what else do I know? H is sine x, good. Well, there was one more piece of information. Oh, this one. This one here, where it touches at one point. It's the tangent of x. Okay? So if this is y equals x, then I'm not going to go there. I'm going to say that this is the tangent of x, this line that touches at that one point, tangent of x. Okay. So here's what I want to say. Oh, okay. You might want this. I want that back too. Okay, small triangle first. X, 1, H. I get sine of X equals H. Great. Now, this one. I see this big triangle, and I say, okay, big triangle has a 1 here, has a question mark here, and an X. What trig function uses opposite over adjacent? Tangent does. So the tan x is question mark over 1. So question mark is tan x. So I know this is tan x, and I know that this is sine x. Great. Is that part okay? Yeah, just wait. Here it comes. So here's what I want to do. I want to say that the area of the small green triangle is smaller than the area of the sector. Remember, a sector is a pi wedge. It's this thing in here. So it's this triangle plus this piece here. And I want to say that that is smaller than the area of our big triangle. Area of the blue triangle. Okay. So let's see what we can see. I mean, you're okay saying that the blue triangle is bigger than the area of the sector, which is bigger than the area of the triangle, right? Excellent. So now let's find these areas. Okay, so for the green triangle, it's 1/2 base times height. The base of this triangle, oh, I'm sorry, this is the triangle I'm considering. That's just the height of that triangle. So, I want that to be a different color. Okay, there we go. Green triangle, big blue triangle, area of the sector. So this little green triangle, the area is 1/2, the base is 1, and the height is sine x. Okay. Now, what about the area of the blue triangle? Well, the blue triangle is this triangle here. It's got a base of 1, a height of tangent. So I'm going to say 1/2 a base of 1 times tangent. Now, what about the area of the sector? Well, the area of the sector, I remember that that's the area of the circle, pi r squared, but it's not the whole circle, it's only part of a circle. It's x radians out of 2 pi radians, right? It's some portion of the area of the whole circle. There's the area of the whole circle, and now I want some percent of the whole circle, like pi over 2 divided by 2 pi. So I'm going to have a fourth of the circle, okay? So there's an x. Now, if the radius in this problem is 1, because we're only in a circle, and we can cancel these. Yep. So now what do I know? I know that I have x over 2. Good? Nice. And we're all still in agreement that the little green triangle is smaller than the pi wedge, which is smaller than the big blue triangle. Okay. So here's what I'd like to do. I'd like to get rid of all the 2's by multiplying everywhere by 2, but I also am going to do at the same time divide by sine x. So I'm going to distribute that everywhere. Okay, here these cancel, sine x's cancel, and I get 1. And here I'm going to have 2x over 2 sine x, and the 2's cancel. So I have x over sine x. And then here, 2 times 1/2, those are going to cancel. And then I'm going to have tangent x over sine x. But remember, tangent x is sine x over cosine x. And then I'm going to divide by sine x. These will cancel, and I'll have 1 over cosine x. Okay, 1 over cosine x. So, what can I say? In the big triangle, 1, what's the cosine here in the big triangle? Oh, in the big triangle, the cosine is adjacent over hypotenuse. And this is 1. Oh, but that's not 1. Get 1 over cosine. What is the cosine of x? Here's x. Cosine. That's not right triangle. Here's the right triangle. Cosine. Come on, little cosine, tell me who you are. This is not 1. This is 1. This is a right triangle. 1 over cosine. I have a note that cosine of x equals 1. Cosine of x equals 1. Oh. Is it here? No, because then that's less than that. It must be the big triangle. This is 1 because of that. That's tangent x. This. Oh, look, Pythagorean theorem. 1 squared plus tangent squared equals the hypotenuse squared. And so 1 plus tangent squared? You remember what 1 plus tangent squared is? 1 plus tangent squared is secant squared. But we want to take the square root of both sides because we're using the Pythagorean theorem. We'll take it this way. Question. This is the hypotenuse. Okay, and it's the hypotenuse squared. Now this is equal to secant squared. And if I take the square root of both sides, secant is the hypotenuse. So 1 over cosine is secant, and therefore that's the hypotenuse. Did that help me? No. Okay, so the hypotenuse is secant x. What would the cosine be here? 1 over secant. No, that still didn't get it for me. Oh, I thought I was so close. Well, clearly, I've made too many videos this morning, and as a result, I can't quite get you to why 1 over cosine according to this picture is 1. But when you get to this point, if you figure it out, please let me know. Because I want to go back here and say, okay, I can prove that's 1. I'm sure I'm going to be able to figure it out. And look what we've got now. This thing that I don't recognize is squeezed in between these two things. Because these things are equal, and this thing is squeezed in between them, and this thing must also have the value of these two things that it's squeezed between. Wait, I think there's something. I know what it is. Right, I forgot. Remember, this is all about as x approaches 0. So if this angle approaches 0, we've got 1 over cosine of x, right? And so if I put a 0 in there, cosine of 0 is 1, 1 over 1 is 1. So that is 1. Okay, so this works as x approaches 0. And so look, behold, this thing we didn't understand is squeezed in between. Come on, you all told me that that pi wedge was bigger than the green triangle and smaller than the blue triangle. So I'm squeezing this thing that I don't know in between two things that I do know. And as x heads to 0, these have the same value. And so this one must also have that same value. Woof. All right. I kind of want to do it again in one smooth motion. Let's see if I can do it. You can stop watching now if you want, but I'm going to do it again and say, I've got this picture. Because I don't want to be beaten by this. And I've got this, and I've got this, and there's a right angle, and this is 1, 0, and there's a little height here, and there's a little height here, and this is x, and we know that this is 1. Okay, so I'm going to say little triangle is, oh, and I need h. So what's h equal to? This is 1. No. this is 1. Right. So I know that h over 1 is the sine of x, so h equals sine x. I know that this length over here, I'm going to call it g for no good reason. I can say that the tangent of x equals g over 1. So I know that g equals tan x. Okay. And then I'm looking at this small triangle, at this pi wedge, and at this big triangle. And I'm going to say the area of the small triangle is less than the area of the pi wedge, which is less than the area of the big triangle. So let's find these areas. We know that the area of this little triangle, and this little triangle goes to here, is 1/2 a base of 1 times, what was the height for that blue triangle? H, which is sine x. We know that the big triangle's area is 1/2 a base of 1 times its height, g, which is tan x. And then the area of the sector is x over 2 pi times pi r squared, because that's the area of the whole circle times what percent or what portion is in our pi wedge. We don't have the full circle here. We only have x over 2 pi's worth. Okay, so here these cancel, and our radius for this circle is 1. Okay, so I've got 2 over x. The next thing I did was to multiply everywhere by 2 over sine x times 2 over sine x times 2 over sine x. All right, so what happened then? Well, 2's canceled, sines canceled, I had 1. And here, the 2's cancel, and I have x over sine x. And over here, the 2's cancel, and I'm left with 1 over cosine x. As x heads to 0, I do direct substitution here, I know that cosine equals 1. So this is 1 over 1, which is 1. Ta-da! I've now shown that this thing is squeezed between those. And so the limit as x approaches 0 of the area of, this is going to be way too small. So I'm going to say the limit as x heads to 0 of the area of the small triangle is smaller than the limit as x heads to 0 of the area of the sector, which in turn is smaller than the limit as x heads to 0 of the big triangle. Okay, these limits are all true. We see in this picture that blue triangle is smaller than sector, is smaller than big triangle. So now what I've got here is that the limit as x approaches 0 of 1, the limit as x approaches 0, and the limit as x approaches 0. The limit of a constant is the constant, and so now I'm able to say that. And because this limit is squeezed between these two equal values, I know, therefore, the limit as x approaches 0 of x over sine x, that must be 1. There, I felt that. Thank you for your patience with that. All right, so sandwich there, we'll see a little bit of in the spring, late March, early April, but for now, that's all I got. So dig into your limits homework, and I can't wait to hear if you have any questions.